Hey there everyone, welcome back to Lead Coding. In today's episode we are going to learn about disjoint set union find. So it's a very important data structure. We can use it at many places. So first of all, we will be learning about the theory, and then we will see the optimizations that we can make. We will see the implementation with the help of an example question, and then we will be solving an advanced question. So the questions that we are going to solve today, the first one is redundant connection and it's a medium problem. Then we are going to solve graph connectivity with threshold, which is a difficult problem. So first of all, let us see what we actually mean by union and find with the help of an example. Let us say we have certain numbers. Numbers are 1, 2, 3, 4 and 5. And we have 5 groups. First group will contain the number 1, second group will contain the number 2, similarly the third group, fourth and the fifth group. So there are 5 groups. Each group contain only one number, and the representative of that group is the number itself. So the representative of the first group is 1, the representative of the second group is 2, for the third group it is 3, then 4, then 5. Okay, now moving forward, let us say we want to perform the union operation between any two numbers, let us say 2 and 3. When we want to perform the union operation, we will look at the representative of the set or the group in which 2 is present. So it is 2, and we will see the representative of the set in which 3 is present, which is 3. Now we will be performing the union between 2 and 3. This will give us a third group which will contain 2 and 3. Now we also want a representative to represent this group. So that could be the representative 2 or the representative 3, which were the representatives of the two groups that we want to unite. So in this case, let us say we are going forward taking 2 as the representative. Now we can get rid of the groups which were there earlier. Now this is our new group with the representative as 2 and the numbers as 2 and 3. Now let us say we want to perform again the union operation between 1 and 3. Now this is same as performing the union between 1 and 2. Why did we replace 3 with 2? It is because the representative of the group in which 3 is present is 2. So we are always taking representatives when we are performing the unions. So performing union between two numbers is same as performing union between the groups in which those numbers are present. That's why we are always going to the representative. Now in this case, a new group will be formed which will contain 1, 2 and 3. Now there are two candidates to be the representative of this new group, 1 and 2 respectively. So let us go with 1 as the representative this time, and we are getting rid of the groups which were present earlier. Now this is the new group with 1 as the representative, and there are 3 elements in this group. Now let us say we want to perform the find operation on the element 2. If we want to perform the find operation on element 2, it is going to return the representative of the group in which 2 is present. So 2 is present in the group represented by 1, so 1 will be the answer for this. 1 will be the answer for 1 also, and 1 will be the answer for 3 also. What if we want to perform the find operation on 4? What is the representative of the group which contains 4? So it is 4 itself. Similarly with 5, if we want to perform the find operation on 5, it is going to return 5. So this was like what actually this union and find does. Now we are going to see how can we implement this in programming. So again, let me create the 5 nodes that we had: 1, 2, 3, 4 and 5. These are the groups, and we can consider them as node, and each node will point to its parent or its representative. So 1 is pointing to itself because the representative of 1 is 1, the representative of 2 is 2, for 3 it is 3, for 4 it is 4, and for 5 it is 5. As they are their own representatives, that is why they are pointing to themselves. Now if we want to perform the union between 2 and 3, and if we want to make 2 as the representative, so what we can do is we can change the connection from 3 to 2. Now the representative of 3 is 2, so this forms a new group in which 2 is the representative of the overall group. Now again, if we want to perform the union between this group and this group, so the representative of these groups are 1 and 2, so we'll be performing the union between 1 and 2. Let us say we want to make 1 as the representative of the final group, so we just have to change the connections from 2, we have to point 1, so 1 is the representative of 2. Now this is the new group that is formed, so we just have to change the connections if you want to unite two groups. Similarly, if you want to unite 4 and 5 and we want to make 4 as the representative of the new group which is formed, so we just have to change the connection from 5 and point it to 4. Now we can see that the representative of each group is pointing to itself. So 1 is pointing to itself, it denotes that 1 is the representative of this group. 4 is pointing to itself, denotes that 4 is the representative of this group. Now if you want to perform the find operation on 3, it should return 1, as 1 is the representative of the group in which 3 is present. So we will be going to the parent of 3, which is 2, and the parent of 2, which is 1, and the parent of 1, which is 1 itself. So as soon as the parent of a node is equal to the node itself, we know that it is the representative. So the representative of 3 is 2. Again, if we want to find the representative for the element 2, we will be going to its parent, which is 1, and 1 will be going to its own parent, which is 1. So 1 is again the representative of 2. If we want to find the representative of element 5, so we will be going to its parent, which is 4. Now 4 will be going to its parent, which is 4. Hence 4 is the representative in this case. Now we want to see the implementation of this, and we can implement union find using arrays. So let us say we have an array and 1, 2, 3, 4, 5. This is the group number 1, group number 2, 3, 4 and 5. Initially they are their own parent, they are pointing to themselves. Now if we want to unite 2 and 3, so if we want to unite them, what we can do is we can make 2 point to 3. So 2 can point to 3, we will just change the value to which it is pointing. Now 2 is pointing to 3, so it is something like this. There are two nodes, 2 and 3. Initially they were pointing to themselves. Now we want to unite 2 and 3, and we want to make 3 as the representative. That is why what we are going to do is we are going to make a connection from 2 to 3, and 3 will be pointing to itself, so 3 is its own parent, and the parent of 2 now becomes 3. So again, if we want to unite this is the node number 4, this is the node number 5, and this is the node number 1. Now let us say we want to unite the node number 5 and the node number 2. So in order to find the union between node number 5 and node number 2, we will have to find the representatives. So the representative of 5 is 5 and the representative of 2 is 3. So it is same as uniting 5 and 3. Now if we want to unite them, and let us say we want 5 to be the representative, so we will just make 3 point to 5. So now 5 is going to be the new representative, and this is the entire new group that we will be having. And we have to change the connections in the array. So the parent of 3 now becomes 5. So in place of 3 it will be 5. So this is how we can use arrays to implement the concept that we studied in the earlier slides. So now let us see the first example using this, and we will see the implementation of this. Also I want to mention that this is just the union find algorithm without any optimization. So the time complexity for this algorithm could be big of an inverse case, because if if you want to perform the find operation, and if the group is very skewed, so the nodes are connected one after another, in that case, in the worst case scenario, we will be jumping to n nodes, where n is the maximum number of the nodes that is present. So in the worst case, it is big O of n. We will see optimizations in the next slides. So before that, we can implement this approach and we can solve one problem using the same. We will come back and we will optimize the approach, and then we will be going to the advanced problem. The problem statement is, in this problem, a tree is undirected graph that is connected and has no cycles. We already know the definition of trees. The given input is a graph that started as a tree with n nodes with distinct value 1, 2 till n, with one additional edge added. So if they add an additional edge, it is going to create a cycle. So our task is to just remove an additional edge so that we can remove the cycle and we can get our tree back. So that's what the question statement is. Now let us see how we can solve this. So let's consider that there are few nodes, node number 1, 2, 3 and 4. So these are the 4 nodes. Now when we have n nodes in a tree, we will have only n minus 1 edges. So if we have anything more than this or anything less than this, then it won't be a tree. The reason is, if there are more than n minus 1 edges, then there will be a cycle, and if there are less than n minus 1 edges, then we won't have the entire graph as a connected graph, which is a condition for it to be a tree. So what we will be doing is, we will be starting with all the nodes as separate groups, and as soon as we are getting an edge, as in the question they are giving us the edge list, so as soon as we are getting an edge, we will, instead of creating an edge, what we will do, we will put them in a same union. So let us say we are getting an edge between 1 and 2, we will be putting them in the same union, we will be grouping them together. Next time, if there is an edge between 2 and 3, we will be putting 3 inside this as well, and we will remove this. Next, if we have an edge between 2 and 3, and as we can see that 2 and 3 belongs to the same union, so initially we had 1 connected with 2, now we had an edge between 2 and 3, so they are in the same union, and now we are getting an edge between 2 and 3 again, so it will cause a cycle in the graph. So we can never have an edge between the elements which are present inside the same union, or we cannot have an edge between the elements which are already connected somehow. So this is what we have to avoid. So what we can do, as soon as we get an edge, we will put these elements into the same union, and if we get an edge between the elements which are present inside the same union, then we will be returning that edge as a redundant edge. Let us see the implementation of the same. So first of all, I am creating an array which is called the parent array. Now we want to know the size. We already know that there are n minus 1 edges, but there is an extra edge, so there are total n edges, where n is the number of nodes which are present. So we will make the size of parent as n plus 1, because I think we will be starting from 1. Yeah, it is a 1 indexed, so we will make the size of parent as n plus 1, and the reason is we will be indexing it from 1 till n. Now initially each node is its own parent, so we will be going from I is equal to 1, I is smaller than equal to n, I plus plus, and we will make parent of I is equal to I, because now at the initial stage all the nodes are in their own separate groups or in their own separate sets. Now we will be traversing our edge list, and we will be uniting these two elements which form an edge. For that we have to write the union and the find as well. So first let us create find. In the find, let us say we are finding the representative of x. So if parent of x is equal to x, that means it is the representative. Otherwise we can call the same function on parent of x. What we are doing here, we are calling the same function recursively. So for example, let us say this is the representative and 2 is pointing to 1, 3 is pointing to 2. So the array will be something like this. For 1 it's the parent, for 2 the parent is 1, for 3 the parent is 2. So if you want to find the representative for the element 3, so 3 will look that what is its parent. So its parent is 2, so it is going to jump on the node 2. Now 2 will look what is the parent of 2, and then 2 will be jumping to its parent, then it will be reaching 1. Now 1 will see the parent of 1, which is 1. So as soon as the parent is equal to the element itself, we are going to return. Otherwise we can call the same function recursively on the parent of x. Now we will be performing the union operation, and we are performing union operation between two nodes a and b. Now we already discussed that when we are performing the union operation, we will have to perform this on the representatives of a and b. So let us overwrite a with the representative of a and overwrite b with the representative of b. So find is giving us the representative. Now what we can do is we can make the parent of a as b, or we can do the reverse, is equal to b. So that's it. These are union, these are find, and now we have to go to each of the edge and we have to unite them. First of all, we will check that if find of a 0, that is the first element, is if it is equal to find of a of 1, the second element of the edge. If it is, that means that they are present inside the same group or the same set. We can return this edge because this is the redundant edge. Otherwise we can unite them and put them in the same union or in the same set. So we have to perform the union operation, and a of 0 comma a of 1. And finally we can return this. It is find. So it is giving us correct answer. Let us try to submit. It got accepted. So in the worst case, the union find algorithm, it runs in big O of n, where n is the number of nodes. So this is an big O of n algorithm, and the extra space that we are using here is big O of n again. So both the space and the time complexity are big O of n. Alright, now let us see slight optimizations into this approach. Now in the slides we saw that when we are uniting two groups, and let us say if the representative of the first group is x and the representative of the second group is y, so we can make either x or y as a representative of the new group. But this approach could be optimized if we make the choice of the representative a bit more optimally. So let us say that the group which is represented by x have 100 elements, and the group which is represented by y have only 2 elements. So we will be choosing the one which is greater in number, the one which is greater in strength as the representative. So this is called union find by rank. So there comes an extra component which is the rank, or which is the strength of each group. So we can see in the code we can create another array which is called rank, and initially we can make the rank of each element as we have to initialize the rank here. Rank is equal to new int n+1, and initially rank of I, each I is equal to 1. The strength or the rank of each of the group is 1 initially. Now when we are performing the union operation, we have to make the choice that whether A should be the parent of B or B should be the parent of A. So if rank of A is greater than rank of B, it means that the number of element which is present inside A is greater than the number of elements which is present inside the group represented by B. So A should be the new parent. So parent of B should be equal to A. The rank of A is going to be increased by the rank of B. So all the elements which were present inside group represented by B, they will come under the group represented by A. So the strength or the rank of A is now going to be incremented with the rank of B. Let us say there were 2 elements inside the group represented by B. Now these 2 elements are going to come under the group represented by A. So the group represented by A had 100 elements initially. Now it will have 102 elements. So if the rank of A is greater than rank of B, that means that there are more number of elements in A. So we are making A as the parent of B, and we are incrementing the rank of A. Otherwise what we have to do is we have to make B as the parent of A, and we have to increment the rank of B, and we can add the rank of A into this. So we can run this. So this is a slight optimization, and this will lead the complexity from big O of n to log n. Now the time complexity is log n in this case. Now we are going to see about the path compression. So what do we do in the path compression is, let us say we have some nodes 1, 2, 3 and 4. Now this is one set, and the representative of the set is 1. So 1 is pointing to itself, 2 is pointing to 1, 4 is pointing to 3, and 3 is pointing to 2. Now if I want to find the representative of 4, I will see if the parent of 4 is equal to 4. The parent of 4 is not equal to 4, it is equal to 3. So we will recursively call the same function on the parent of 4, which is 3. And we will check if the parent of 3 is equal to 3. And in this case it is equal to 2. So we will recursively call and we'll come to 2. Same is the case with 2. The parent of 2 is 1, and we will recursively call it to 1. Now in this case the base condition will be strike. So we will have the parent of x is equal to x. So 1 is going to be returned. So 1 will be returned here, and 2 is going to return 1 here, and 3 is going to return 1 here, and finally 4 is going to return 1 as the representative. But when we are returning this, we can set the parent of these elements at the same time equal to 1. So what I'm trying to say is, if I make the parent of x is equal to find of x, so what we are doing here is we are making the parent of 2 as 1, making the parent of 3 is equal to 1, the parent of 4 equal to 1. So the final configuration that we are going to get will be something like this. So this will be the final configuration in which all the elements are pointing to 1 now. the parent of 3 is also 1. So now instead of going through 2, 3 is directly connected to 1. Instead of going through 2 and 3, 4 is directly connected to 1. So the next time when we are making a query and we want to find the representative of 4, it will be a constant time solution. Same with the 3 and same with the 2. So this is how we are optimizing in terms of time. So when we combine the path compression and union find by rank, we can say that time complexity is almost constant, but in the worst case we say that it becomes log n solution. So the question is, we have n cities labeled from 1 to n. Two different cities with label x and y are directly connected by a bidirectional road if and only if x and y share a common divisor strictly greater than some threshold. More formally, cities with the label x and y have a road between them if there exists an integer z such that the following conditions are true. Z divides x, z divides y, and z is greater than the threshold. Given two integers, n and the threshold, and an array of queries, you must determine for each query if a and b are connected, and we have to return the answer in the form of an array as true or false. So what actually is it saying? Let us say we have 6 nodes and the threshold is 2, when the queries are coming as 1, 4, 2, 5 and 3, 6. Now there are only two numbers, which are 3 and 6, which are connected in this case. And why are they connected? Because they have a common divisor, and the common divisor is 3 for 3 and 6, which is greater than the threshold. So there is only one connection between 3 and 6, and for the query 3 and 6 we are going to return true, for the other queries we are going to return false. So this is the graph that we obtain. In this case, as we see that the threshold is 0, so there's always one divisor between two numbers, and that is 1. So 1 is always there and 1 is greater than the threshold. That is why all the nodes are connected to all the other nodes, and for all the queries we are going to return true in this case. Let us try to build another example. Let us say we have 1, 2, 3, 4, 5 and 6. Now we are keeping the threshold as 1, so anything which is greater than 1 can be the common divisor. So for 3 and 6 the common divisors are 1 and 3. So 1 and 3 are the common divisors for 3 and 6. So we can actually connect them because 3 is greater than the threshold, which is 1. For 2 and 4 the common divisors are 1 and 2, and 2 is greater than 1, which is the threshold. That is why we can connect them as well. For 3 and 4 the common divisor is 1. For 4 and 5 it is 1. For 2 and 6 the common divisors are 1 and 2. That is why we can connect them. So this is the final graph that we obtain. I think other than that we cannot connect anything else. We cannot connect 1 and 5, 5 and 3, 5 and 4. Yeah, so this is the final configuration of the graph. So do you think is it necessary to find pair by pair that what all are the divisors for these two numbers? Well, instead of doing that, we have another trick. Let us say that we have 1 as the threshold, so we are starting with 2 being the divisor. So 2 is the divisor for 2, for 4, for 6. Yeah, we will not go beyond 6. Then so 2 can be paired with 2, 4 and 6. So 2 being paired with itself means nothing in this case, and 2 can be paired with 4 and 2 can be paired with 6. Now we will be starting with 3 being the divisor, and we will see the multiples of 3, which are 3 and 6. So 3 can be connected with 3 and 3 can be connected with 6. So we are making a connection between 3 and 6. Now we will be going to 4 and we will see the multiples of 4, which is 4 and 8. Now 4 will be connected to itself and 4 will be connected to 8, but 8 exceeds the limit of numbers that we have. That's why we are not going to make any connections. I think we got all the connections using all these elements. Similarly, we would have gone to 5 and 6 as well. The multiples of 5 are 5 and 6. 5 and 10, and it will also not make any change. Then 6 is 6 comma 12, and it will also not make any change. So we will be starting with a number which is just greater than the threshold, and we will be going to its multiples. And let us say if the number is x and we are going to the multiples of x, we will be making connections between x and those multiples. So this is an easier way to construct the graph. So when we are making the connections, we are actually putting them in the same union. And finally, we can either connect them using a graph, but then it would require us to perform the BFS to find whether 4 and 2 are in the same component. So we will have to perform the BFS, which will be some extra computation. So we will just keep them as a union instead of constructing them as a graph. We will keep them as a union, and we will simply we will apply the find operation for two elements which we want to perform the query for. So we can start with implementation, and things might become more clear once we start implementing it. So first of all, we will be performing it without the rank. We are creating a parent array. It is almost same. Just create the parent array, and parent is equal to new int of size n plus 1. Now making each of these node point to themselves, starting from I is equal to 1, I smaller than equal to n, I plus plus. Parent of each node is the node itself. And then we will take the I is equal to the threshold t plus 1, I is smaller than equal to n, I plus plus. We will take a multiple m, initialize it with 1, and while m multiplied by I is smaller than equal to n, we will perform the union operation between I and m plus plus. Finally, we have to perform the find operations. So we will be going to each of the query, and if now we can simply insert answer dot pushback. Answer is the array that we want to return, and we will make it a boolean type array. Vector of bool answer dot pushback, find of a0 if it is equal to find of a1. It means that if both a of 0 and a of 1, if they belong to the same, if their representative is same, or if they belong to the same group, then we are going to return true. Otherwise we are going to push back false. Then we can return the answer. Before this, we have to create the union and the find. So let us create the find first. For any integer x is if parent of x is equal to x, return x. Otherwise return find of parent of x. Now performing the union operation. Union int a int b. First of all, we will have to overwrite a with the parent of a or the representative of a, which is find a, and b with the representative of b, which is find b. And now we will make parent of a as b. So this is it for the union operation. Let us see if it gives us the correct answer. True, true, true. It should be true, true, false. False, false, true. Union is if parent of x is equal to x, return x. Find parent of x. Okay. And parent of a is equal to b. Correct. No int of n plus 1 point to themselves. I plus 1, I is smaller than n, I plus plus, m plus plus. We have to perform the union between these two. Yeah, so we have to perform the union operation between I and I multiplied by m. And now it should give us correct answer, false, false, true. Let us try to submit this. It is giving us TLE, and we already saw that there is space for the optimization. First of all, let us try to do the optimization in terms of path compression only. We are not going to perform the rank as of now. Let us see that if we will be able to get the answer accepted with the help of the path compression only. Okay, let us try to submit. It is getting accepted with the help of path compression alone. We can add the other optimization, which is the rank. We just have to make a rank array and then initialize it here. New int of size n plus 1, and at each index we have to put the rank of I as 1. And we have to make changes in the union. So if rank of A greater than the rank of B, in this case what we have to do is we have to make the parent of B as A, and we have to increment rank of A plus equal to rank of B. Otherwise we have to perform the reverse operation. Make parent of A as B because the strength of B is more, and add to the rank of B the rank of A. So this is union find by rank. In the line number 22, I think there are more number of nodes. We should make this as a long type, I think. Let us try to run this case. Okay, so as we are getting the runtime error because we are adding the ranks, what instead we can do is we can just increment the rank of B with 1 and here the rank of A with 1. So I think this should also be sufficient. This will always keep the component with more element ahead, not by the difference of number of nodes, but just by a certain value, but it will keep the one which have more number of nodes a bit ahead of rest of the nodes. So that's what we can perform here, and it works. So I think this should be enough to learn the concept, and I will provide some more questions in the description that you can perform after going through the video. And just keep practicing, practice questions on code forces and on LeetCode. On LeetCode there are very few questions from union find, but there are a lot of questions, a lot of variety of questions on code forces for the same topic. You can go there and solve those problems. I will provide the link in the description for the important problems that I have solved using this. If you like the video and if you want videos for more such concept in future, please subscribe to the channel, like to the video, and please leave in the comment section your opinions and your advices for improvement. Thank you.